Hey everyone, welcome back, and today let's solve Leetcode problem 64 titled Minimum Path Sum. So we're given an m by n grid filled with non-negative numbers, and we need to find a path from top left to bottom right which minimizes the sum of all numbers along its path. And note that we can only move either down or right at any position in time with any cell, as long as it's, again, of course, within bounds of our input grid. So in example 1, we have the input grid to be the following. They also give us an image to better visualize and depict how it would look like. And they actually highlight the path that we would need to take to minimize our path sum, only going either down or right for each cell that we traverse. So in this case, we output a minimum path sum of 7. Why? Because we start from our top left cell, which would be 1, and we go either down or right to reach, effectively, ultimately, our bottom right cell, which in this case is also 1. So we go from 1 to right 3, to right 1, then down 1, then down 1, and the path sum of all of those cells that we visit is going to be 1 plus 3 plus 1 plus 1 plus 1, which is equal to 3 plus 4, which is 7, and that is the minimum path sum that we could take to reach our bottom right cell. Theoretically, yes, we could go from 1 to 1 to 4 to 2 to 1, and we still would not be breaking any of the rules, only going down to right and going from the top left cell to the bottom right cell, but that does not minimize our path sum because we need a sum of 4 plus 2 plus 1 plus 1 plus 1, or in other words, 9 to actually reach the bottom right cell, taking that path. And obviously, 7 is less than 9, and we're trying to minimize our path sum, and so for that reason, we'd output 7. In example 2, we have an input grid of the following 1, 2, 3, 4, 5, 6, and we output 12 because that is also the minimum path sum to actually reach the bottom right cell, minimizing our path sum, which in this case is going to have a value of 12. So for the constraints, we see that the length of our input grid is going to be m, and the length of our input grid at index I is going to be equal to n. And we see that the dimensions or length and columns of m and n are going to be within the range of 1 to 100, not exceeding those values. And the grid at any index I, any index j, or any cell value in our grid is not also going to exceed 200. It's going to be in the range of 0 to 100, to 200. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so if you guys haven't realized that, we're going to use dynamic programming to solve this problem efficiently, where we simply have to break this problem down into specific subproblems that involve taking the minimum value of two cells. And those two cells are going to be the down cell and the right cell. Basically, the two cells that we can hit or traverse through from the current cell, kind of following the problem's criteria, right? Only going right or only going down at any cell or point in time in our input grid, right? Minimizing our path sum, right? So to do this like we usually do for our dynamic programming problems, we're going to have a DP table where DP at any index I, any index j is going to represent the minimum path sum to reach that cell ij from our starting position, which is going to be the top left corner, grid at index 0, the top left cell of our input grid. Right? So for the instantiation, or rather initialization of our DP table, DP at index 0, is simply going to be grid at index 0, right? It's simply going to be the starting point that we start traversing from, or our beginning cell. And for the transition or population of our table, for all of the cells in the first row, notice how following this problem's criteria, we can only go to these cells in the first row by coming from the left, right? Just going right for each cell. We can only come from the left of it, and that's perspective. And for all of the cells in this first column, we can only come from above, right? Just going down one. So for all of these cells in the first column and row, we can only actually access those cells only going right, or rather only going left and only going from above, right? Following this problem's criteria of going only down or right from each cell that we're traversing. And for all the other cells that we have to calculate the minimum path sum for, it's simply going to be the minimum of the values of the cell above it, which would be I minus 1j, or the cell to the left of it, right, which is going to be I, j minus 1, kind of emulating or stimulating that down or right process for any cell at any point in time, right? It's going to be that plus the current cell value, which is going to be the current cell value of grid index I, index j, the current cell value that we're looking at to expand our minimum path sum to potentially use it to reach our last, or rather goal cell, right? And so the final result of our input, or rather of our algorithm, is going to be stored in dp at -1, -1. Why? Because that is going to be the bottom right or last kind of cell in our dp table. It's going to be the right or bottom right corner or bottom rightmost cell of our table, which in this case is going to be 1, right? So with that out of the way, let's just go ahead and dive straight into the code here. And before we actually start kind of populating our table here, or rather our dp table, I'm simply going to get rows and columns to be equal to the length of a grid and length of grid at index 0, like we usually do for our dynamic programming problems. So just access these values a little bit easier rather than having to type them out manually, just for optimal purposes, right? Not in big O complexity, but just in typing forms. So yeah, right, pretty simple. We can access it later on when we need to. Now, I'm actually going to overwrite my original input because that's not going to use extra memory. And for the current status that we're in this problem, we don't actually need to create an extra dp table to use extra memory of our input grid. We can simply overwrite and change or modify the values of our input grid itself as we break this problem down into subproblems and kind of compute values at the current cell for future values, right? Instead of having to make a whole new table, right? So first, let's populate our first row like we talked about before. So I'm going to say for I in the range of the first from 1, starting until the number of rows we have, which we initialize on line 3, for I in the range of 1 up until the number of rows we have, we're going to set grid at index I, index 0, I'd probably say, to be equal, or rather plus equal, to grid at index I minus 1 at index 0. What are we doing here? Okay, we're simply iterating through all the cells in the first row, right, at index 1. And for each cell in this first column, rather, not row, we have to update the value of this current minimum path sum of its current value and the value of the cell directly above it, right? And we're simply accumulating the path sum for all the cells in the first column as we can only move downwards. Sorry, I did not mean rows, I meant columns. We're populating all the cells in our input grid of the first column. Sorry, we can only move down, and so we're simply adding the previous cell value to go up until that ith cell to kind of instantiate it with I minus 1, 0, right? To reach index I, index 0 in the first column, it's going to be the same value of index I minus 1, 0, right? That current value plus the value before it, right? Because the value before it tells us how much sum we need to actually reach the value up until that index, and so we have to add that value of our current cell value to actually populate it accurately, right? And we're going to do the same thing for the first row. So for I in the range of 1 up until the number of columns we have, we're going to set grid at index 0, right, because this is the first row, at index j. All right, sorry, should be j, not I, as my iterator, at index j, to be added on to the cell right to the left, right to the left of it. We're simply extending the path sum for this current cell in the first row. So index 0, j minus 1, right, the cell to the left of it, right? It's really same logic here. It's simply going to be for the first row rather than for the first column. So once we've actually instantiated or initialized the first rows and columns to actually reach all the cells in those specific indices in our input grid, now we have to cover all the cases for the other values. So into this, we're going to do a nested loop to iterate over all the other values in this input grid. So for I in the range starting from 1 up until the number of rows we have, and for j in the range of 1 up until the number of columns we have, simply nested loop to go over all the different cells in our input grid. This is the key part of this dynamic programming solution. We're going to set grid at index I, index j, again the key part of our program, to be equal to the minimum of grid at index I minus 1 and then j, this first cell, okay, and then the other value that we have to take the minimum of is going to be grid at index I, j minus 1. And rather than setting it equal to the minimum of these values, we're going to add it to this current cell to basically stimulate the minimum path sum up until and including this index current value plus the value before and the minimum of those two values to use this in our current path sum to minimize that value. Right, we're simply adding the minimum of the down and right cell and adding it of the current values cell to, or the current cell's value to extend it and include it in our minimum path sum. Because again, essentially for every single cell, the value at that cell is going to tell us the minimum path sum to reach that specific cell. And we're simply extending this current cell's value to our minimum path sum to see if we can actually reach the bottom right corner with the minimum path sum that we have. And we simply have to return now grid at index -1, because that's going to store the sum that we need, the minimum path sum that we need to reach the bottom right corner. Right? In other words, it's simply going to represent the minimum path sum to reach the bottom rightmost corner of our grid, the target cell. Right? So as you can see, if I submit this, unless I made any syntax errors here, this should be accepted. And as you can see, this is just about as efficient as you can get. So to kind of reiterate, what does this code do overall? We're simply just modifying the grid itself. We're overriding the values in our grid. In other words, so we don't actually need any extra memory here. It's going to be a constant time solution, right? So by the time we actually populate our grid up until the last value, right, taking the minimum of the down and right cell, as the problem statement says right here, then we know that grid at -1 is going to contain the minimum path sum from the top left cell to the bottom right node of the grid, right? And we simply have to modify the grid in place to, again, save memory and keep the code efficient, right? We're simply storing the minimum path sum for each cell, breaking it down into its individual subproblem of adding its current value to the minimum of the two values, or rather two cells before, right? The down cell before and the right cell before, right? So for the time complexity of this solution, this is going to be a big O of m times n solution, where again m is the number of rows and n is the number of columns, because we really only process each cell once as we iterate over all of the cells and find the minimum path sum for that specific cell. And the space complexity is going to be big O of 1, or a constant time solution. Why? Because we simply modify the grid in place, and we're not actually using any extra data structures for storage of our input. We're simply just overriding or rewriting our input grid itself for every test case. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.